All right, so in this video, we're going to follow up the video where we learned about electric flux. And here, we're in Gauss's law, we're going to apply what we know about electric flux. And when we do that, we're going to get to Gauss's law. In this video, we won't apply Gauss's law, but we'll be ready to, and there are other videos for you to watch where you can see how that's done. Okay, so what is Gauss's law all about? The idea is that if we have some sort of distribution of charge, that's why I have a question mark here. We don't know. It could be a couple of individual point charges. It could be a sphere of charge. It could be a plane of charge. It could be a cylinder of charge, anything. The idea of Gauss's law is that we take a surface that will enclose that charge distribution or the charges. And then we're going to look at the electric field at points on the surface in order to find the total flux through the surface. What we're going to eventually find is that Gauss's law gives us a relationship between the field on the points on the surface and the total charge that's inside the surface. This is going to be a really useful way to allow us to find electric fields expressions due to charge distributions, and it's going to be a way easier than the integration you saw in Chapter 5. Okay, so we're going to look at a couple situations, and basically what we're trying to get at is learn some basic facts about flux and closed surfaces so that we can sort of come to a conclusion. Now, in this situation, here is my surface. My charge is over here. We know that electric field lines point away from a positive charge. And so here you see the electric field lines being shown. And those electric field lines go through the surface. Now, over here, the electric field lines are going into the surface, but the area vectors are pointing out away. Remember that the area vector for a surface is perpendicular to the surface itself. When it's a closed surface, it points away from what volume is enclosed. So that's why I know that dA is in that direction. So the field lines that go into the surface give a flux that is negative. But on the other side, the electric field lines come out of the surface, and those give an electric flux that is positive. What ends up happening is the total flux through the surface is zero because some of the flux is negative and some of it is positive, and they cancel each other out. Here's another scenario where the electric flux is zero, but it's a different situation. Notice in this case, the charges are inside the surface. Here's my surface, that shaded area. I have a positive charge and a negative charge inside of there. Positive charges create electric fields that go away from them. Negative charges create electric fields that go towards them. So over here, we have flux that is negative because of the negative charge, but over here, we have flux that is positive. So actually, in this scenario, even though we have charge inside the surface, we still have a total flux of zero. So it is different from the previous picture, but it still gives the same result. Notice that if we added up the positive and the negative charge, they cancel each other out. So that might be a clue. The total charge inside the surface is zero, and the flux is zero. That would have applied to the last case as well. All right, now here are two different surfaces. It's hard to see the second surface. I'm outlining the second surface. I think you can see the first surface. Here what we're trying to see is that the flux through both these surfaces is the same. The reason being, if we remember, the electric flux is a product. Well, it's a dot product of the electric field in the area. But for surface 1, the electric field is stronger and the area is smaller. For surface 2, the electric field is weaker because you're further away from the charge, but the area is larger. So as the electric field and the area change, they change in an inverse manner that allows for the flux to be the same. It seems what you could start to surmise here is that the area doesn't matter. Okay, now we want to look about something about the flux and the charge that's inside the surface. Again, remember negative charges have electric fields that go towards them. And so in this case, the electric flux is negative because the electric field goes into the surface, but the area vectors are pointing away. So they're anti-parallel, so they're going to give a negative dot product. Here, the difference in the second picture is that we have more charge, which gives more electric field lines. And so the amount of negative charge gives you more flux. The flux is still negative because the electric field lines are going into the area, but there's more of them, so the flux is larger. So we can say negative charges are inside the surface. We have a negative flux, but it's also going to be proportional to how much negative charge there is. Here's the opposite situation. What if we have positive charge inside the box? Electric field lines go away from positive charges. So here, the electric flux is positive because of the electric field lines, and the area vectors tend to be in the parallel direction to each other, or at least the angle between them is less than 90. If we double the charge, we get a larger electric field, so we're going to get a larger electric flux, but it's still going to be bigger than 0 because it's passing out of the area, it's going out through the area. Okay, so again, now we see that for positive charges inside a surface, you get a positive flux, and the flux is proportional to the amount of charge inside. These are all conclusions we're making. The last thing another thing that we want to talk about is the size of the surface. I already covered this in another picture, but just to reiterate, if I change the size of the box, it's not going to affect the electric flux, again, because the smaller box will deal with stronger electric field, but smaller area. The larger box has a larger area, but a smaller or weaker electric field. So the flux stays the same. And so what we conclude is the flux does not depend on the size of the surface. Okay, so let's summarize what we found so far. The sign of the charge will determine the sign of the flux, and that is the charge that's inside the volume. So if you have positive charge inside of the surface, you have a positive flux. Negative charge inside the surface, you have a negative flux. If you don't have any total flux, if the net charge is 0, or if there's no charge inside the surface, then there's no flux. So we can definitely see that there's a relationship between the electric flux and the charge that's inside the surface. Now we're going to look at a specific situation where we're going to find the flux, and we're going to do for a point charge. This is going to give us an important conclusion that is actually going to be really helpful, and it's going to give us what we call Gauss's law. I'm going to find the total flux through an area for this point charge. Now it says I'm going to choose a spherical surface, and I am. So I'm going to imagine surrounding it by a sphere. It has a radius of r. Why am I going to do that? There's a couple different reasons. These are the electric field lines. This would be the dA right here. What we're going to find that in general, at any point on that sphere, the electric field line is going to be parallel to the area vector. And so what that means is I can change this dot product into just a a multiplication of two scalars, because implicitly what we're saying is the dot product is equal to E times dA times the cosine of the angle between them, but we're talking about the cosine of 0, which is just equal to 1, and that's how we get this value. There's another thing that's important. We know that the electric field, due to the point charge, is only related to the distance away from the charge, and the magnitude of the charge, of course. So the other thing that's happening is on the surface of the sphere, the electric field is constant. So I can take it outside of the integral. It's just a constant. Now, if I integrate dA over the entire area, I just get the area. This ends up to be the surface area of a sphere, which is equal to 4 pi r squared. There's a little bit of geometry formulas that you might want to keep in mind and remember while we're doing this. Okay, so I got E times A, but our electric field was KQ over R squared. Our area was 4 pi R squared. The R's cancel, and I get 4 pi KQ. This looks like kind of a mess. But remember, the other day I told you that K can be written as 1 over 4 pi epsilon naught. That's going to be useful right here. So 4 pi, and instead of K, I'm going to write 1 over 4 pi epsilon naught times Q. And you see that that disappears, and I get Q over epsilon naught. This is actually the general form of Gauss's law. We found that the total electric flux through that surface was equal to Q over epsilon naught, where Q was inside the surface. And this is what we call Gauss's law. We did it for a special case, but it's actually true in general. Whenever we take a closed surface and we find the electric flux that passes through the surface, the total flux will be equal to however much charge I have enclosed over epsilon naught. What we'll do in class is we'll look at some applications of that and how we can use that to actually figure out electric fields. But that's going to be in class and in another video.